discussion on wear and surfaces. Okay, and now we're going to talk about an analytical approach to calculating wear. But we'll find out that even this approach is not super accurate. Okay, and that this approach cannot replace testing for more accurate data. If you have a specific application in mind that you think is susceptible to wear, this approach cannot replace the testing. It is useful, though, for us to think about in terms of the things that should be considered in treating wear. Okay. And the reason that we don't have a super accurate approach is because wear is related to friction, and friction is still something that we cannot calculate super accurately. We do have models, and there's a lot of research that's been done, but to date we don't have something that we can just pull out of a book and pull out wear and friction. But it's still informative for us to think about the things that govern the wear behavior and the wear rate. So around the 40s, a wear rate equation was used, and they said that the wear rate is delta over T, and delta is basically the thickness of material lost, and T is time. So basically, if you had some material and that material was wearing, and say that amount of material wore off, this would be your delta, and if it wore off in that much time, then your wear rate would just be that amount of material over that time. Pretty straightforward, right? All right. This could also be expressed as the wear rate can also be expressed as K, which is our dimensionless wear coefficient, over the hardness of the material times the surface interference pressure, P, times the velocity, V. Okay, and K is dimensionless. Okay, there's no units associated with it. It's a dimensionless wear coefficient. Okay, and that dimensionless wear coefficient is based upon the material or the materials that you have in contact with each other. H is the hardness. Okay, and in this case, the hardness is measured in megapascal. Okay, but the hardness values are often expressed in terms of mass per area. Sorry. Okay, so to convert to megapascal, you'd have to multiply by gravity or whatever factor for the British units. All right, so P is the surface interference pressure, Okay, it's also often it's in units of pressure. For an SI, it's megapascals. And then V would be your sliding velocity in units of length per time. Okay, so that would be your wear rate. It's important to note that the wear rate is length or distance related. Okay, not as much velocity dependent. Okay, what that means is, although we have expressed this as velocity, what we really are concerned with is the length that the surfaces slide relative to each other over a certain amount of time. But the length is what dominates, not the actual velocity. Okay, so another way of thinking about this is, if you had something running at a constant speed for a certain amount of time, then you could put your velocity here to get your wear rate. But the right way to think about it is that it's length dependent, even though these units are velocity. So if we have like two objects, say object A and object B, that are sliding relative to each other, and that's, you could say that this one, say, is stationary, and if this was A and this was B, the wear rate we could write as the wear rate of A. So if we wanted to calculate the wear rate of A, the wear rate of A would be our wear coefficient with respect to materials A on B over the hardness of A times the interference pressure between A and B times the relative velocity between A and B. So that's how we'd actually calculate the wear rate between two objects. Incidentally, though, although this is the historical way of looking at it, when we calculate wear, what's often done is we look at the wear volume, and this is a more common way of expressing wear, and that is the volume of material removed. Okay, so this is a more common way of expressing it. And so in this case, we'd say the wear volume, okay, and this is in length units cubed, and that wear volume is equal to our wear coefficient over the hardness of the material that we're trying to investigate the wear with respect to, times the force, and then that would be the force between the two materials, times the distance. Okay, so this would be the force between two materials, and this is the distance that they travel. Okay, so this is the analytical method of looking at wear, but it's not necessarily, this approach is not necessarily super useful if we're trying to look at like the dimensional change. Okay, So say that this is not super useful when we want to know how much material is actually removed, right? So if we're looking at two objects A and B that are wearing relative to another, what we kind of want to know is how much material is worn. And so to do that, what we can do is we can actually look at the height of the material. Okay, so we'll call this the height of the material, and this is done just by dividing the wear rate over the apparent area. Okay, and the apparent area, okay, is the nominal area, okay, just from what we can look, just the width of times the length of the object in contact with each other. Okay, so this would be the volumetric wear rate over the apparent area. Okay, and in that case, we can just say that that is equal to our wear coefficient over the hardness times F times S times 1 over the apparent area A. Okay, or KFS over HAA. If we want to look at the actual amount of material moved, and this would be, say millimeters or inches or whatever units of length that you're using. The values for K, okay, so K, our K values have large variation. Okay, in fact, they are 2 to 4 times has a range of 2 to 4 times the calculated value. Okay, so we have a table here. We can look up the wear coefficient for different materials. But even though we have these values, the reality is that they are there's quite a bit of variability in there. But it sort of does give us a scale. Okay, so this is from the book, and these are the wear coefficients, and notice that they're the estimated wear coefficients. Sorry about that. And so this is your adhesive wear, your abrasive wear, and your fretting, and we have coefficients for each. And you can see that there's pretty wide variation between them. Another thing to notice is that the larger values are here closer to the origin of this graph, and these are identical metals here, so this would be the same. So they have some of the worst wear. If you have compatible metals, you have less worst wear, and then you have your partially compatible. And if you remember, these come from the wear features between materials, and we talked about the adhesive wear of those materials in a previous talk on surfaces. Okay, so this concludes the discussion on wear and calculating wear. Okay, and it's important to note that testing is still required to have a higher degree of confidence in your design. Okay, so if you have something that you know is going to wear, this approach can get you close to looking at how your dimensions might change as it wears over time, but they won't be necessarily super accurate. And if you want them to be more accurate, then you're going to have to actually do some testing. And as indicated in the graph, if you have the same materials and you add some form of lubrication to reduce the wear between those materials, you get huge variations in values. Okay, this is 10 to the minus 2, this is 10 to the minus 6, and all this is if you have identical metals with good lubricant. What's also interesting to note is that if you have a good lubricant, that a material that you might think wouldn't perform well because it would be the same material and same material, and so it violates sort of that design consideration. When you add lubrication to that same system, that you get, you know, as good of performance as dissimilar materials that are in there. And obviously, if you would run out of lubrication, then you'd have much higher wear, and so that's what often happens. You know, when engines seize up, as we mentioned before, you have similar materials, and when the lubrication is gone, then the wear dramatically increases. All right, so that concludes our discussion on wear, analytical wear, and next we're going to talk about Hertzian contact.